All right, let's go ahead and get started. We hope you're enjoying your spring break. We're going to post these problems because we do want you guys to study just a little bit over break. Sometimes Chem 110 can be like that friend who shows to the party that you really don't want to have there. You don't want them there, but they keep coming back, and coming back, and it's kind of annoying. And sometimes Chem 110 can feel like that, especially over spring break. You want to enjoy yourself, but you know that when you come back, you have a very hard exam to take. So you do want to prepare. You also want to enjoy yourself, kind of in a dilemma. But this is how we're going to prepare. We're giving you guys these problems for a reason. We want you to do well. We want you guys to succeed in 110, even if we're not in person. So I'm going to go over 4 of the major problems that we kind of worked through clickers and through your homework and in other book topics that I think will help you succeed on the next exam coming up at the end of the month. So we're going to go and get started with an Arrhenius equation using graphical methods. Basically, what we're doing here is kind of like the Chatelier equation where we're using linear regression t-tests to find a slope and then apply that to an equation. In this case, it'd be the Arrhenius equation. So let's go ahead and look at the problem. A study was conducted over the temperature of 20 degrees Celsius to 30 degrees Celsius, looking at fireflies flashing at a rate that's temperature dependent. So the first thing we should see before doing any math, before making lists in our calculator, is that temperature is in degrees Celsius. We have an issue. We need to make temperature in degrees Kelvin. So we're going to go ahead and do that. So I'm going to make this list 1. I'm going to make K list 2, list 3, and list 4. So we already know that this has to be in degrees Kelvin. To get from degrees Celsius to degrees Kelvin, we just add 273.15, right? So I'm just going to write that in here, plus 273.15. What I'm going to do is I'm going to go ahead and go on my calculator. I'm going to press stat, and I'm going to go ahead and go to my list. And if you notice, I've already done this, but I'm going to clear it so I can work it out with you guys. So what we're going to do on list 1 is we're going to make everything already in Kelvin. So if you look, I just did 20 plus 273.15. That would be 293.15. And then I carried it down. You just add 2 each time. So you have 295, 297, 299, 301, and 303. So go ahead and make your list 1 degrees Kelvin so you don't have to edit that. And then we're going to do K, just leave it as K in row 2. So we're going to have 0.24, 0.26, and if you realize it increases by 0.02 every time. So go ahead and enter your K values in. And then list 3. So what we know when we're doing an Arrhenius equation using graphical methods goes in list 3. List 3 should be natural log of K. Remember, we're graphing natural log of K versus inverse temperature. So if ln of K is in list 3, what needs to be in list 4? You got it. 1 over temperature, and temperature needs to be in degrees Kelvin. And luckily, we've already converted to Kelvin, so don't have to worry about that. So list 3, to get this to natural log, we're going to press enter. And we're going to do natural log, which if you don't know where that's at, it's right down here by the 4 button. Natural log, and then we're going to do natural log of list 2, because list 2 is our K, right? You should all get negative values because a natural log of a whole number is going to be a negative. And then list 4 we know is 1 over temperature. So I'm going to press enter and do 1 divided by L1, because L1 is our temperature in Kelvin. So when you do this, if you get correct values, you should get values of around negative 1.427, negative 1.347, negative 1.273, negative 1.204, negative 1.139, and negative 1.079. And then for column 4, you should get 0.0034, 0.00339, 0.00337, 0.00334, 0.00332, and 0.0033. Those should be your 4 lists. Again, you can leave this as degrees Celsius and make a whole new list for Kelvin. I prefer to do it right away in Kelvin, but that's up to you. So now, just like Chatelier back in Unit 1, we have to look at the linear regression t-test. So you go ahead and press stat, and you scroll over to tests, and if you're on the TI-84 plus, it could be the C, it could just be a TI-84 plus, it will be option F, linear regression t-test. Go ahead and press enter. So now we look at what we're graphing. So when we're doing the Arrhenius equation with graphical methods, we are graphing 1 over temperature and ln of K. Temperature values will always go on the x-axis in this case, and our temperature value will be list 4. So we're good. List 4 should be on the x, and then y, our only other list available for graphing, would be ln of k. So we're good to go. Let's go ahead and calculate. Now we're looking for a slope value. We know from basic algebra y is equal to a plus bx. What is the slope value? Is it a or b? It's going to be b because whatever is tied to the x is always going to be our slope value. So if we scroll down, we look at b is negative 3090. I'm going to write that down. B is equal to negative 3090, which is equal to our slope. We're done with calculator regression t-test right now. So we have our slope value. How do we find activation energy from our slope value? Well, we look at the Arrhenius equation. I'm going to write the 2.4 in the Arrhenius equation out. I'm more familiar with that. You can also do the regular form that we learned in lecture. They will both work. So the 2.4 in the Arrhenius equation looks as such. So I'm looking at this. I need to find out which of these values equals my slope. And in this case, negative EA over R is equal to B. So let's set those two equal. Negative EA over R is equal to negative 3090. What I should notice right away is these negatives would cancel. Those become positive. What else do we know about this equation? We know that R is a constant. R is what in units of what? R would be 8.314 joules per mole Kelvin, right? It's in joules, not kilojoules. And this equals 3090. So then to solve for activation energy, I would multiply 8.314 by 3090, and I would get an activation energy of 25,690 joules per mole. That is correct. If you got that answer, you are correct, but we want then a more applicable number. I would convert this to kilojoules per mole. So we would just divide this by 1,000 to get to kilojoules. Again, you're not incorrect by doing 25,690. We just want it in a smaller number so it's easier to work with. 25.7 kilojoules per mole would be the more correct answer. So that's how you solve for activation energy using slope and linear regression t-test analysis. A follow-up question to think about would be, how would you solve for A? What is A to start out with? A is the frequency factor. So if you write out the Arrhenius equation in its normal form, K is equal to A E raised to the negative EA over RT, right? We know EA now. That's 25.7 kilojoules per mole. We know R, it's a constant, and we know temperature, and we know K. We're solving for A, right? We know temperature and K from this graph. If I pick 30 degrees Celsius or 303.15 degrees Kelvin, I know that K is 0.34. This is kind of like method of initial rates back in the last unit, where you can pick any data column and go with it, plug it in, and you can solve for A. That's a good follow-up question. You're more than welcome to solve that. I am not going to in this video, but it would be something to practice to get familiar with before the exam. All right, good. Moving on to Le Chatellier's principle. So if you noticed in working the homework, Le Chatellier's principle really isn't a mathematical concept. It's more or less we want you to get the concepts. So let's go ahead and take a look at this chemical reaction. I have 2A plus B goes to 3C plus 2D. So let's work through these three problems. Addition of a blank or removal of a blank will cause equilibrium to shift to the right. Addition of something will cause equilibrium to shift to the right. Well, let's take a guess. We have two guesses basically, reactant or product. You have 50-50 shots. It's kind of like roulette at a casino. You got almost a 50-50 shot here of getting it right. Let's pick reactant. So if I add reactants, right, which ones are reactants? Right or left? Which ones would be reactants? It'd be this side. If I add more to this side, so I have a seesaw. If I add more to this side goes down, right? So now this side is sticking up. I have to add more to this side to balance it out, right? Because this side's lighter, so I have to add more to even this out. So if I add a reactant, it will cause equilibrium to shift to the right, correct? Because we need to add more product to balance this seesaw out. So if I add a reactant, what else could I do with a removal to make the same change happen? Removal of a product, right? Le Chateliers Principle is just a seesaw effect. Again, I'm going to run through that one more time. If I add a reactant, so the left side of the seesaw goes down, that makes the right side lighter and goes up, right? So I need to make more right side, which in this case would be our products, to even out the seesaw. In an endothermic reaction, adding heat would shift the reaction towards blank, which would something Kc. Let's write out our reaction again. I'm just going to make this clear. 2A plus B is in equilibrium with 3C plus 2D. So an endothermic reaction, what do we know about endothermic reactions? An endothermic reaction has a delta H value greater than or less than 0. It'd be greater than. Is heat a reactant or a product in endothermic? Think about it. In an endothermic reaction, do I have to add heat to the system, or does the system give off heat? I add heat. So if I'm adding heat, it has to be a reactant. I add heat to the reaction to get this going to products. So in an endothermic reaction, as seen here, adding more heat would shift the reaction towards right or left. Well, again, let's look at our seesaw effect. So I'm adding more heat. I'm adding more to the left side. So this side gets heavier on the seesaw. So now this side is light and sticks up. I have to add more to this right side, which hence means I would have to add more products to even out the seesaw. If I add more products, what does that do to Kc? Well, let's think. Kc is what over what? Kc is products over reactants, right? Kc is equal to products over reactants. If I add more products, what's going to happen to Kc? If this number becomes bigger, if it was originally 1 over 1, and now it's 100 over 1, what happened to Kc? It got larger. So Kc would increase. That's a very good problem to think about. Lastly, in the reaction above, decreasing volume would shift equilibrium to the side with blank moles of gas. Whenever you decrease volume, you always shift to the side with less moles of gas, which in turn would shift the reaction to the left or right direction. Well, let's look. Which side has less moles of gas? We have 2 here, and we have 1 here. So we have 3 moles of gas on this side, right? And then we have 3, and we have 2 here. So we have 5 moles of gas on the right side. Which side has less moles of gas, left or right? Left. So it would shift in the left direction because there are less moles of gas. These are 3 really good concept questions to think about before you take your exam in 2 weeks. Kind of getting a notion of how the seesaw effect works, what's going to happen to Kc, which way is equilibrium going to go. Think about different chemical reactions as well. It doesn't have to be this one every time. You can make your own reactions and think about which way this is going to go depending on what you do with the reaction. Okay, now I want to get an equilibrium. If you've noticed, equilibrium has been the bulk of the past 2.5 weeks. We're going to work through 2 equilibrium problems today. This first one is pretty straightforward. The second one is very challenging if you don't know your equilibrium rules. So let's go ahead and start on this first one. So I'm given a chemical reaction right here, and I'm given initial pressures. So let's go ahead and rewrite our chemical equation. Nitrogen plus oxygen goes to 2 nitrogen monoxide. Initial change equilibrium, right? We've all seen this. Ice table is very basic way of setting this problem up. So I'm given initials. Let's fill in all the initials. 4.4 for nitrogen, 4.4 for oxygen, and 1.1 for nitrogen monoxide. I'm given a Kp, and we're given ATM. That's good to go because Kp deals with pressures. Kc would be dealing with concentrations. In this case, we had partial pressures, so Kp would be correct. We don't have to convert anything right away. But this is where ring directions comes in key. Calculate the new equilibrium partial pressure, so we're just calculating the E column, of each component after an additional 0.4 ATM of NO is injected. So we have to add 0.4 ATM right away, right? That's just coming from the problem. we're adding 0.4 to the original 1.1. So this would equal 1.5. So now we have all of our initials. Now we have a decision to make. Is the reaction going to go left or is it going to go right? We can't just assume because these are bigger, it's going to go this way, and this one's smaller, so it's going to come to that one. You cannot make that assumption. How do you find which way the reaction goes? You look at Q. Q is also known as the reaction quotient. It's like the snapshot of where the reaction is at in time. Q is closely related to K. It's not the same, but it's the same way of solving. It's products over reactants. So let's look. What do we have for products? We have nitrogen monoxide at a concentration of 1.5. And our two reactants, we have both at concentrations of 4.4. What you should notice is I'm missing one thing. This 2, the stoichiometric coefficient of 2, plays a significant role in Q and K. Whatever that coefficient is, you have to raise it to that numeral in the Q equation. So in this case, I have 2 here. These are both 1, so these are both raised to 1. If you would run the numbers on Q, you would get a value of 0.116. Okay. I still cannot make my decision on which way the reaction is going, because I have to compare K and Q. So let's go ahead and do that. K and Q. Q is equal to 0.116. K is equal to 0.06. K is significantly less than Q. Whenever you compare K and Q, whichever way this arrowhead points is the way the reaction is going. So in this case, since K is less than Q, the reaction is pointing left because the arrowhead points left. So what does that mean for my constituents? Is this going to be disappearing or reappearing? Well, if we're going left, from right to left, these are probably going to be appearing, right? Because it's going that way, while these ones are disappearing because it's receding. So minus 2x plus x plus x. Again, stoichiometry is key here. Always look for stoichiometry. We had a 2 here. We could change our value by 2 times x. These ones are both 1, so we change by 1 and 1. And now you just add. So we'd have 4.4 plus x, 4.4 plus x, and then 1.5 minus 2x. I just carried those values down. So now we can find our x value, right? We need equilibrium partial pressures. We have them, they're just in terms of x. So we need to find out what x is. Let's look at Kp. Kp is 0.06. Kp, just like Q, is equal to what over what? Products over reactants. So I have a product, 1.5 minus 2x. Again, it's squared because we have that stoichiometric coefficient of 2. And then we have our reactants, 4.4 plus x, 4.4 plus x, right? Now, you can do this by hand if you want. I prefer the solver function on the calculator. If you have the TI 84 plus C, I'm going to be working through it with that. If you have the 84, you can go ahead and consult the recitation manual, as there are steps on how to solve it using that. So we're going to go ahead and press the math button, and we're going to scroll all the way down to the bottom, and it should be option B. It's called the solver. So we have E1 and E2. E1 is always going to be what your K value is. So I'm going to type that in, 0.060. Now E2 is just all of this. Make sure you have parentheses around your numerator and denominator. So I'm going to do my numerator. 1.5 minus 2x, that squared. It's not 1.5 minus 2x squared. It's 1.5 minus 2x parentheses squared. We're not squaring just the 2x. We're squaring the whole thing. And parentheses for the numerator. Now we go to the denominator. If you notice, this is just 4.4 plus x times 4.4 plus x, or just 4.4 plus x squared. So I'm going to do that. So parentheses for the denominator, and then 4.4 plus x squared. Again, we're not squaring the x, we're squaring the whole thing. Enter. Okay, so now that looks good. Let's scroll down. When you're taking your exam, when you're doing your homework, make sure you always zero this out. This will already have a number from your last run. Go ahead and just press 0. That clears it, and it sets your x value to whatever all of this is going to be equal to. And then to solve it, you don't press enter, you press the alpha button, it's the green button on the TI-84, and then enter. And you get an X value or a change value of 0.1881. So X would equal 0.1881. So I need equilibrium partial pressures, and I have them in terms of X, and I have X. So let's solve. N2 would be equal to 4.4 plus X, so that would be 4.4 plus 0.1881, which is equal to 4.588. It's the same thing for O2, right? 4.4 plus X was the same for both, so these are both going to be 4.588. And then for nitrogen monoxide, we're going to do 1.5 minus 2 times the X value, 0.1881. And that would equal 1.124. So now we have equilibrium partial pressures. We're done with the problem. That's a very simple, basic, kind of straightforward equilibrium problem. These should look very familiar to you, and that should have been rather easy if you've been keeping up on equilibrium. Now we're going to go into a much harder one. I think this one's very difficult. If you don't know equilibrium concepts well, you may struggle with this. If you want to, feel free to pause the video and go ahead and work this by yourself. It's a good test to see how much you really know about equilibrium. But I'm going to go ahead and start working out right now. So we're given in the problem 3 moles of NH3, 2 moles of nitrogen, and 5 moles of hydrogen. Right away, before even reading the problem, we should notice something wrong. When we're doing equilibrium, whether it's, let's just think about Kc. We have moles. What's wrong with that? We need concentrations, right? So to get a concentration, you need units of molarity. Molarity is moles per liters. We have moles. Now we need a liter value. Luckily, if we keep reading, we have a liter value. So before doing any math or doing any equilibrium calculations, let's convert everything to a molarity. This will be step 1. So we have 3 moles of ammonia in a 5-liter container. That would be 0.6 molarity. Same thing for nitrogen. We have 2 moles of nitrogen in a 5-liter container. That would be 0.4 molar. And then we have 5 moles of hydrogen in 5 liters. That would be 1 molar. Right, I'm just converting everything to molarity using moles divided by liters. That's a concentration unit. We learned those in unit 1. Now, what's the next thing you should notice? We've worked through the problem. We noticed that there's a temperature value. Sure, that might be significant. Determine the equilibrium concentration. The equilibrium concentration. Why does that make a difference? Well, we're given Kp. Kp will not work with concentrations, right? Kp works with partial pressures and units of ATM, torr, whatever units. But in this case, we need this Kc. We have to convert this Kp to Kc so that we can work in units of concentration. How do we do that? Well, we have a formula. Kp is equal to Kc times RT raised to the delta N. So let's go ahead and fill in what we know. We're given Kp, right? 41.4535. We're solving for Kc, right? That's our unknown. We don't know Kc. R is the ideal gas constant, 0.08206. And the temperature is given to us in degrees Kelvin, so I don't have to convert anything, 900. Now delta N. What does delta N? If we think back to the ideal gas equation, PV equals nRT, what did N equal back then? N was equal to the number of moles. It's probably going to be the same thing here, right? Delta N would be the number of moles. Whenever you have a delta, it's always final minus initial. So that would be final minus initial. So products minus reactants. Let's look at that. We have a 1 here and we have a 3 here. 1 plus 3 is 4, right? So we have 4 final moles. How many initial moles? We have 1 reactant, so 2. So we have a delta N of 2, right? Final minus initial. 4 minus 2, so we have a 2. If you run the numbers here, you would get a Kc value of 0.0076. right? So now we're good to go. We have concentrations and we have a Kc. So we can do step 3, which is to set up our ice table. What's the first thing we do in an ice table? We rewrite our chemical equation. All right, very basic ice table setup that we did like the last time. Now let's fill in what we know. So we have 0.6, we have 0.4, and we have 1. Okay, everything's there set up. Now we need to solve for equilibrium. It's just like the other problem. We have to make a decision on which way the reaction's going. We cannot just assume one way or another. How do we make that decision? We look at Q. Q is products over reactants, right? So let's look at my products. I have 0.4 and I have 1, and my reactants are 0.6. What am I missing? Stoichiometry. I have 1 and 2, so 0.4 raised to the 1. I have 3 H2s, so I have to raise this to the third. Luckily, it's still 1 because 1 raised to the third is still 1. And then 0.6. 0.6 should be raised to the 2 because there's a stoichiometric coefficient of 2. So Q would be equal to 1.11. Now let's look at K versus Q, right? K was equal to 0.0076 and Q is 1.11. K is less than Q. Which way is the reaction going, right or left? Well, the arrowhead points left, so we better be going left, right? Whenever you're comparing K to Q and the arrowhead points in one direction, you're going that direction. So does that mean my right side is going to be positive or negative? It's going to be negative, right? Because if we're going from right to left, that means that these are decreasing and this is appearing. So that'd be minus x, minus 3x, and plus 2x, right? Again, I'm just looking at stoichiometry. 2, 1, 3. And now we just carry them down. 1 minus 3x, 0.4 minus x, and 0.6 plus 2x. Again, I just added those values down. So now we need equilibrium concentrations. We have equilibrium concentrations. They're just in terms of x. So what do? I set them equal to k. K was equal to 0.0076. Products, 0.4 minus x, 1 minus 3x, 0.6 plus 2x. What am I missing? Yet again, stoichiometry. This needs to be cubed, and this needs to be squared. Just like Q, we do the same stoichiometry where we raise it to that number each time. And again, you're more than welcome to work these out by hand. It would save you quite a bit of time to do them with your math solver function. Again, if you look on the last problem, I did that in front of you. I'm not going to do it this time, just not to be redundant. So if you would solve this, the x value would be 0.216. If you didn't get that x value, go ahead and pause the video and rework your math. You most likely had a parentheses error somewhere in your calculator, but go ahead and rework it. Make sure you have, when you enter it, a parentheses around the numerator and the denominator. That might be your issue, but you should get an x value of 0.216. So now we have equilibrium concentrations in terms of x, and we have x. So what do? We plug in x. So NH3 would be equal to 0.6 plus 2 times our x value, and you would get 1.032 molar. Same thing for nitrogen. Nitrogen was 0.4 minus x, so 0.4 minus 0.216 would be equal to 0.184 molar, and then hydrogen. Hydrogen was 1 minus 3x, or 1 minus 3 times 0.216, and you would get 0.352 molar. That was a very tough, kind of intricate question. We kind of threw everything at you here. Converting Kp, converting moles to molarity, looking at ice tables, using your math solver. I mean, this literally has everything you could possibly throw at you in an equilibrium problem. So if you understood this, you're probably on the right track. If not, it's okay. Go ahead and take a look, pause the video, rewind it, and try to get this problem down. All right, and the last two problems we're going to work through are very simple acid-base problems. They're good to know. I mean, it's not anything intricate, but they're very good starting building blocks for acid-base learning. So we're looking at H3PO4. Which of the following is not a conjugate acid-base pair present? If you remember back from Chem 109, what is H3PO4? What kind of acid is it? Is it strong or is it weak? It's a strong acid. It's one of our 7 strong acids. So we're just going to write that down. H3PO4, strong acid. Now applying this to Chem 110, what do we know about a strong Bronsted-Lowry acid? What does it do? It donates a proton, right? Strong acids donate protons, and the bases would receive or accept the protons. So let's write that down as well. It donates a proton or an H+. It's the same thing. A proton H+ are the same. So we have H3PO4, and it's aqueous, so it's reacting in water, right? What is this going to make? Let's think about this. The H3PO4 is a strong acid. It's going to donate an H+. So this H donates one of its protons to water. What happens to this molecule? We lost an H. It's going to be H2PO4 now, right? We went from H3 and we lost an H+. I'm going to fill it in. H+ is gone. So it goes and donates that to hydrogen or H2O. It becomes H2PO4. This was originally no charge, right? There's no negative, there's no positive 2, whatever charge on this molecule. If I lose a 1 charge, what does this become? If I was at 0 originally and I lose +1, 0 minus 1 is equal to -1, right? That's why I have a minus here. And then what would happen to water? We gained a proton. If we gain a proton in water, it becomes H3O, right? H2 plus 1 proton would be H3O. And what I have to do the charge. Originally, water is net neutral. We have 0 charge, and I added 1. 0 plus 1 would be plus. If you notice, H3O plus is the hydronium ion. But we're not done. What's significant about H2PO4 minus? It is also an acid. So we have H2PO4 minus plus H2O. Again, very similar to the top one. Let's think about it again. H2PO4 minus is the acidic character here. H2O is the basic character. What's going to happen to H2PO4? It's going to donate a proton. So if this donates one of its H's, what is this going to become? HPO4, and what's the charge going to be? We were originally at -1, and we lost another 1 because the proton left. So -1 minus 1 would be 2 minus. And then again, you would form hydronium ion because the H2O accepted a proton from the acid. Again, we have yet another acid. HPO4 2 minus plus H2O. What's going to happen here? Same exact thing as the top two. This is going to become PO4 what? 2 minus, lost a proton, so now it becomes 3 minus. And you form yet again hydronium ion. Now we're done, right? This can no longer donate a proton. If you know this is phosphate, the base for phosphoric acid, so we're done. So which one of these would be your correct answer? It'd be option D. These two are not present. H2PO4 does not directly go to PO4, right? H2PO4 went to HPO4 and then phosphate. It did not directly go between these two. It's a good question to think about stepwise associations of a triprotic acid. Again, it's a triprotic acid because there's 3 H's to give off. 3 tri, that's where we get the name. All right. Then the last question here, which of the following is the strongest base? So we know bases are in terms of K what? We've already seen KC, right? Equilibrium. We've already seen KP, same as equilibrium, right? KC is concentrations, KP is pressures. What about KB and KA? Are they any different? Mathematically, no. It's going to be products over reactants, right? Because that's what K is. K is just products over reactants. But in this case, KC would be relative to concentrations, KP would be relative to partial pressures, and then KB would be relative to bases, Ka relative to acids. Again, K is always just products over reactants. It's just what you're working with, which is denoted by this subscript. In this case, we're working with KBs because we want the strongest base. So we need everything to be in terms of KB. So this one is good, this one's good, and this one's good. We have an issue. These two are in Ka. So what do we do to convert a Ka to Kb? Well, we have an equation we can use using the dissociation of water. We have Kb times Ka is equal to Kw. Kw is just the dissociation of water, and you have Kb and Ka. Kw is always going to equal 1.00 times 10 raised to the negative 14. That never changes. Kw is always 1.00 times 10 to the negative 14. So let's go ahead and work through option G. We have 1.00 times 10 to the negative 14th is equal to, I have my Ka, 4.9 times 10 raised to the negative 10th times Kb. Right? I'm just applying this formula to this problem. I would divide this over, and I would get a Kb of 2.04 times 10 raised to the negative 5th. Right? Now we're in terms of Kb. We're good to go. Same exact thing for this one. 1.00 times 10 to the negative 14th is equal to my Ka, 1.1 times 10 to the negative 2nd times Kb. Again, divide this over, and you have a Kb. In this case, it's 9.09 times 10 raised to the negative 13. So now everything is in terms of Kb. We need the strongest base. Is the strongest base going to have a higher or a lower Kb? It's going to have a higher. Again, the larger association is going to be a higher Kb. So we want the smallest negative exponent, right? The larger positive exponent would mean larger number, and the smaller negative exponent would mean a larger number. So we need the smallest negative exponent. So we have negative 8, negative 5, negative 5, negative 9, negative 13. We have a tie with the negative 5. So we have option G and option H. This number as a decimal is just this. This number as a decimal is just this. Again, I just wrote these numbers from exponential form to decimal form, so it's easier for you to see which one's larger. Is 204 or 180 larger? 204 is larger, so then option G would be our correct answer. Right? All I did was I converted everything to Kb, then I looked and found the smallest negative exponent, then you're done. So that is it for working through the major problems, kind of basic stepwise problems for you guys to look at over break. Again, I hope you're enjoying your spring break. It should be time to have some fun, but also do not forget about your upcoming exam when you get back to classwork. It's going to be challenging, and I hope you guys are reviewing over break, but don't push yourselves too much. Again, do enjoy yourselves because it's time to get away from school for a little while. That's it for now. We will definitely post more problems later. Enjoy the rest of your week.